Mr. Eason.
Hi, morning.
Oh, hi, I'm here now.
All right, brilliant. Okay, we're going to start very soon. There's just a couple of people still joining us. The number's slowing down now, so I'm sure everyone will be here pretty soon. I'll just give them one more minute or so, and then we'll get going. Okay, so we're going to start. Good morning, everyone. Good to see so many people here. We'll start with kind of the boring parts, really, expectations. But you know, I think it's important we just run through those quite quickly, just to let you know what you're getting yourself into. If you do continue and choose to join us for maths, and in a little while we'll get on to some doing some maths, doing a little bit of maths. In the time we've got. So just to clarify, we follow the Edexcel course. So, you know, sort of all your books, exam revisions should be based around that. It is very tricky, it's very challenging, but obviously you get a pretty good reward out of that. You know, an A-level in maths is very well respected, and you know, can lead you to obviously the next stage beyond A-levels. And it's quite important for a lot of courses at university, and you know, and other places look highly upon it. We've got a few components. So we have the core element, which is the algebra. So you know, most of the work there is algebra based, building on your knowledge from GCSE and making things a little bit more difficult, more challenging. New concepts as well coming in, but some of that core stuff that you've sort of done at a higher level GCSE is really, really important as well. We have applied parts, which is statistics and mechanics. So, you know, you do have to spend a fair bit of time on those, looking at data, you know, analysing data, doing different calculations and probability with statistics. And mechanics, looking at how things behave, really, how particles colliding with each other, being pulled around, and all different forces and things like that work. It's important you're equipped, so you need to get yourself a good calculator. The one I recommend is the one listed there, the Casio FX991. That's kind of the white and black one. I'm sure lots of you have seen that around. So if you haven't got one of those already, I would recommend you get that one. It's somewhere between 25 and 30 pounds. Usually the supermarkets have a sale on over the summer, so look out for that and grab yourself one. There are more expensive ones available that I know some other schools, like ask you to get, which do a little bit more, but you'd be more than happy with this one. Some other calculators there, you can pay like £200 off for them. But the benefit of them for your GCSE is kind of a little bit minimal. But if you really want one of those, go for it. But that one, I would say, is probably the best, and most students use that one. We'll have a transition task, so look out for that. You should be receiving details about that, and obviously you need to bring that back and make sure it's completed by your first day back in September. And you will get a test quite soon after starting. One of the first few lessons, just a baseline test, testing that GCSE knowledge that I talked about earlier, really, the vast majority of that. One bit that comes into the statistics part is there is a large data set. So you'll receive this, as you start the course, and you can basically ask questions about it. So you have the data set before the exam. You can look through it and pick out key bits of information, and then in the exam they might ask you questions about it, and you have to sort of do calculations and answer questions about the information that's in that data set. But that's to be covered another day, really. As a rule, we don't issue books, but we do have some recommended books that you can use and will be available to get you started. But we find most students want their own book so they can work through it in their own time. So again, it'll be the EdXL ones, so look out for those and try and pick those up. And I say, try and get at least the year one books. You need a blue book, which is the core aspect, and the brownie coloured book, which is the applied parts. At least get the year one before you start. You'll need the year two ones at some point during year one as well, so you could pick those up at another slightly later time, but I'd say get the year one ones straight away. We need detailed folders, so as we're going through all the topics, you need to be highly organised, making sure you've got all your notes and making sure that everything you're keeping up to date with all the exercises in the books, all the questions, all the homeworks, and all that kind of stuff. Bringing your own device will be useful, just for accessing things like exam solutions, physics and maths tutor, or even just looking up a formula book or something like that. And expect homework. It says there every lesson, but probably not every lesson, but quite a lot. Expect to be doing a lot of work. You're going from maybe like 12 or so subjects now, you're in that region, to 3. So, the work you would have usually got for maths is going to be sort of 3 or 4 times as much. Okay. Right. Just another bit on folders. There's a real big push on this, so please, be organised. We're going to need these things in your folders. Have these ready for sort of day one. You start off being organised. It makes it easier as you're going along. So you have a front cover which basically guides you through the course. You can update it regularly, ticking off the topics you've done. Good to have some keywords and definitions. You get a formula book, so that'll be given to you, and that will need to be used a lot during your lessons. It builds up on that, so the early stages you probably not need it quite so much as we're reviewing a lot of the high level GCSE stuff, but as we start moving on, you'll need that formula book very regularly. If there's any intervention, you need all that detailed in there. And then the main bulk of the folder would be the notes. So you need to keep those in nice order in chapters. All the exercises you've worked through. Make sure you've checked the answers, you've marked them, and all that stuff. And make sure that all the homeworks are in there. Just keep it all nice and together. It makes it easier to revise. Same with the applied. And obviously, other things that we will be doing, tests and exams, you should keep all those. Any past papers you've done that you can use to reflect on and things like that. Okay, so what we're going to do is a little bit of maths now. So I've sort of waffled on for sort of, I don't know, 7 or 8 minutes now. If there's any questions as we're going along, please put them in the chat. I'll do my best to answer them. If not straight away, I can put it onto Teams afterwards. But we're going to look at differentiation from first principles. So for most of you, this would be a completely new topic. There may be some of you who've come across it before. And if you have, don't give the game away too soon for everyone else. But most of you, it should be completely new. So we're just going to recap a little bit of function notation, just because it's kind of related. I just want to make sure we're happy with that. So we got this function here, x squared. So f of x is equal to x squared. And then that function can act on any number, any term, any letter, any expression that we put in that bracket. So just really a reminder here that if we want to do f of 5, that means do 5 squared. And obviously 5 squared is 25. If we want to do f of minus 2, we're just doing minus 2 squared and getting 4. And then we start, putting some letters in. Oh, maybe we just want to do f of a. Well, that would just be a squared. And maybe we want to put a little function in there. So we've got f of x plus 4. So that basically means we replace the x, and we've got right at the top there. So this x over here, we just replace that with x plus 4. So you can see we get that x plus 4 squared. But of course, we can multiply out that bracket and get to x squared plus 8x plus 16. Okay, and just for minus x as well, it's actually a straightforward one as well. We're just going to get x squared. So hopefully that's just a little reminder saying, oh yeah, I remember function notation, so I can kind of see what's happening there. All right. So differentiation is all about the gradient, the rate of change, how something changes. So looking at a graph in particular, most of them are some kind of function, a quadratic, a cubic, or whatever. Some kind of function where we have a curve, and we're interested in what the gradient is at certain points. Its rate of growth, or I guess decay if it's going down. And what we should know about the gradient is if we take 2 points and construct a right-angled triangle, then we can simply work out the gradient as some people might call it the rise divided by the run, or up divided by across. I'll just put that on there. Rise divided by run. I'm sure a few of you heard that before, or up divided by across, or something along those lines, whichever words you kind of use. And we just find the gradient. You say, okay, problem with the curve is that's not, let's say the gradient at those particular points on the curve.
Mr. Eason.
Yeah.
Is it first run then rise, or is it first rise then run?
You mean for the division of the gradient?
Oh yeah.
Yeah. So the gradient, as it says there, the difference in y's over differences in x, or we call it in rise over run.
Okay, so rise first, then run first.
Yeah.
Oh, okay, thank you.
Okay, so that's giving us a gradient. And as I said, you might use some different words or language for that, but that's sort of what you would have done for y equals mx plus c and anything else, any straight line that you've got. Now, if we're going to find the gradient now, go back a little bit. I might want to know what the gradient of this curve is at maybe this particular point here. And what I've done with that triangle would kind of be an estimate, but it wouldn't necessarily be exact. We might get lucky and it's exact, but it's kind of unlikely. So I'm interested in perhaps, where I put that red dot, what is the gradient at that precise point? You might think, well, we did something at GCSE where we drew a tangent and we worked out a gradient of that. And say, okay, well, that'd be fine. If you can draw a perfect tangent, but there's always going to be an element of error there. Okay, so we do have an algebraic method that we're going to work on, but it does revolve around this bit here. You can see I've got the x and the x plus h here. So there's kind of a gap between whatever that x value is and whatever the next one is, x plus h. And the idea is I've got to make that gap as small as possible. Okay. If I make it so small, then I'm really, I'm right around that dot that it's going to be really, really accurate. Okay. So the idea is that that value of h is super tiny. You can imagine we've zoomed in, microscopic levels, if you like, and the distance actually between x and x plus h is super, super small. And that's kind of the key thing for this. So we're finding the gradient. Right, here we go. So I'm going to look at this x squared. This is just a part of x squared that I've got drawn here, the blue line. And I'm looking at part of this gradient here between, well, you can see it's between 3 and 4, but it's between x and x plus h. Let's imagine we've zoomed in, it's really, really small, it's x and x plus h. So what I'm going to do is, this is super tiny, but excuse my right angle triangle there. I'm going to use this right angle triangle here. Now, the difference, we've got the y coordinates, and I'm going to need the difference between those, and then I'm going to need the difference between the x coordinates. Okay, so I'm looking basically for this rise again here, divided by the run. So the rise is going to be whatever this y coordinate is over here. So that's kind of, I'll just pop a line on there. In line with that bit, take away whatever this point is here. Ignore the numbers because we're not really interested in the numbers at the minute. So it's going to be that top, whatever that top y value is, minus whatever that bottom y value is. So the top y value is going to be whatever the function is at this point, x plus h. And the bottom y value is going to be whatever that function is when it's x. Right. And then I've got to find the difference between those. So this is where I'm at really. If I put x plus h into the function, remember the function up here is x squared, I've got this x plus h all squared. Take away, and if I just put x in the function, well, it is just the function, it's just x squared. So you can see this top line here, I've got, that's my rise, x plus h all squared minus x squared. And the run along the bottom, well, the run along the bottom is the easier one really, because it's just the difference between the x plus h and the x. So it's x plus h minus x. Okay? Now what we're going to do is we're going to expand and simplify this. As you see, we've got that bracket on the top, and we can see the bottom simplifies quite nicely. So I've expanded the top bracket there, the x plus h all squared, which is x squared plus 2hx plus h squared. And I've still got the minus x squared from over here. And then the bottom, well, the bottom is just going to be h, because we've got x plus h and take away x. And if you think about it, that makes sense, doesn't it? Because the difference between x and x plus h is just going to be whatever h is. Okay, so sort of made a little bit of progress. But I think we can see here, or I hope you can see, that x squared minus x squared, they're going to cancel each other out, so we can get rid of those. Now, if we have a look what we've got left here, hopefully you see, well, I could take out a factor of h on the top, and then we could simplify those there. The h's are going to cancel out. And I'm just left with 2x plus h. And that's nearly the whole thing. But if you remember what I said at the start, h is so small, it's like microscopic. It is whatever the smallest number you can think of is, it's smaller than that. Okay? So it's 1,000 times smaller than that. But this h here actually, pretty much represents nothing. Okay, so much so that we're just going to say it is nothing. And basically, the gradient of x squared will be given by this function 2x. I'm just going to look at it a little bit more. So what we would do is say, well, there's a limit. There's a limit as h tends towards 0. So we'd put that in front of it. If h is 0, it just ends up being 2x. So my answer is that the derivative for x squared differentiated is 2x. So, okay, so we've done something. We've started with one algebraic function. We've got another. Okay. So what's the beauty of that? Well, that means I know the gradient at any particular point. If I want to know the gradient at 3, well, the gradient is 2x. So if x is 3, well, 2x, 2 times 3, that's 6. If I want to know the gradient at 1, well, 2 times 1, that's 2. If I want to know the gradient at 3/4, we can do 2 times 3/4. So that's 6/4. That's 3 over 2. That's 1.5. You can work out any gradient along that curve using that function. Okay, so basically, yeah, anywhere on x squared, if you want to know what the gradient is, you're just going to use 2x. Put your x coordinate in. Okay. So you might notice the little variation of the notation there. We have our function f of x is x squared. Its derivative here is this f prime or f dash of x. So with the little dash, that means we've differentiated it. We've found the gradient function. Okay. So I'm going to go through another little one with you, just to give you a little bit of another example. Hopefully this will make sense if you're thinking, kind of hard, but not sure. Hopefully this might. So this function is obviously it's a little bit different. It's still a quadratic. And we're not limited to quadratics, but it's kind of easy to start off with a quadratic. So this function is 2x squared plus 1. And this is basically what we're working out. So it looks quite daunting, it looks quite a lot, but a lot of what we got there is quite basic maths. It's just doing a new thing with it. So if this is my function, f of x, 2x squared plus 1, remember the top of the fraction there is the difference in the y coordinates. So that's my f of x plus h minus my f of x. And the bottom is the difference in the x coordinates, which is my x plus h. Put that in bracket just to sort of signify that's the first one, minus the x. So we're doing the same thing here. So imagine we've replaced this x here with x plus h, and this x here would be replaced with x plus h, and we end up with this first term here. Okay. The second term on the top is, it's even a lot easier because it's literally just the function, it's just the f of x. And the bottom, hopefully you can see that the bottom is always going to be h, because it's just going to be x plus h minus x every time. So it's always going to be h. We can always not bother with this that I've written over the right hand side here at the bottom, and just h. Once I've done that, it's a matter of doing what we did last time. It's, can we do some algebra? Can we simplify things? Can we multiply out brackets, collect like terms, and just simplify things down and organize things? So obviously, first step is another color just to emphasize that point. Is expand this bracket here, which we've got there. Ooh, there we go. Practice drawing with this pen. So we've got that expanded there. And then we're just going to continue working through. You can see on the next line, well, all I've really done is multiply it by 2 with that bracket. And I've removed the brackets. I've multiplied out the brackets. Okay, and what can we do from there? Well, I've got a 2x squared minus a 2x squared. I've got a 1 minus a 1. We cancel those out there. See where we've ended up. Obviously, well, again, a little bit of factorising. We've got that h in both terms on the top. If we do that and factorise, we can cancel those h's out. And we've got down to 4x plus 2h. And again, we have this limit as h tends to 0. If h is 0, 2h is still going to be 0. So we're just left with the final answer that the derivative is going to be 4x. Okay. So hopefully, you know, the second example, that kind of makes a little bit of sense. Just something to notice there, that it's a little bit annoying to keep writing it out, I know, and we'll be complaining about that, but look, I wrote that out at the front on every bit coming down here. Okay, because you want to make sure that remember that the limit as h tends towards 0. You know, examiners expect to see that as well on every bit of line of working out. And you know, as you get more confident, you might do slightly less working out stages. So you might expand the bracket and multiply by 2 all in one go. And, you know, collect your terms, cancel the h out in one go. Maybe only do 2 or 3 steps rather than all this. But we want to be thorough to start off with and make sure we're getting all the points. Right. So just to recap, in general, the derivative or differentiating f of x, this is our sort of go-to formula. This is what we're going to do. We're going to get what the function is at x plus h minus the function at x and divide by h. We're going to do all that simplifying, all that, you know, sort of nice collecting terms, good stuff, making it as simple as possible. Okay, so a couple questions on the next slide I'm going to ask you to have a little go at. So if you can just have a little work through these and see if you can come up with a solution to a few of them. We won't have time to do them all, so just pick out 1 or 2 and see if you can pop some answers in the chat or give me a shout if there's anything you want clarifying. Okay, so just give you a couple of minutes to have a little try at that. if it's still a little bit unsure, I've put the starting point up on there. Hopefully you can see that. So that's the starting point for question 1. Let's see if we can get us get into what the gradient function would be. Okay, guys, it's awfully quiet. Anyone got an answer they're willing to share with us? Or
Is question number for question number 2, would the answer be f dash x equals lim h arrow 0 6?
So basically 6, yeah? Question 2?
Yeah.
Yeah, absolutely, yeah. Well done. Sorry, I can't see who that is, but whoever is, well done. Yeah, question 2.
1. I have an answer for question 1.
It would indeed be 6. Yeah, so when we get to our final answer, we can drop the limit h tends towards 0 because we've effectively removed the h when we get to our our very last step. But yeah, fantastic. So first answer, that one would be 6. Anybody got any others?
Question 1.
Yeah, question 1.
Would the answer be 10x?
Fantastic, 10x, awesome. Yeah, well done. All right, so we got a couple of right answers there. I'm sure There are some more out there, yeah. So a little bit more time on that. That would simplify down to 10x in the end. And does anyone have any more before I start giving any more answers out, just out of interest?
Question 3. I've got one for question 2.
So you're a little bit quiet on that one, but go for it. I'll try and hear.
Question 3, would it be minus 12x raised squared?
Absolutely fantastic. Well done. All right, so that would have taken a little bit longer to do because it's a cue that you probably, not too bad, but it would have taken a little bit longer. So yeah, that one ends up being minus 12x squared. And I'm just going to put the rest up then. So we've got a few good answers there. Hopefully a few, got one or we're pretty close to getting one. So this one would be 2x minus 7. This one would be 3x squared. And then we're into sort of more algebraic ones down here. But this one would be 10. And this one here would be 0. And this one at the bottom would be 2x. Okay. Oh, we had a find is 2x right here. Yeah, fantastic. Okay. So yeah, so some good answers. You've got 4 of those between us in that very short amount of time. Don't worry, we're obviously a bit short on time this morning to a normal lesson. It's a little bit different. You wouldn't be expected to get all these done in that amount of time. So if you've managed to work your way to sort of one of those answers, or if you've managed a bit more than that, brilliant. But if you managed to work your way to one of those, you're doing pretty well for this morning. So we found the gradient function there. I'm just going to leave that there for a minute. Let's let you look at that for a moment. Is there anything that you can spot? Is there anything that, sort of between what our function is, what our question is, and what our gradient function, our derivative is? Obviously going down for the rest of them. Is there any kind of pattern or something going on there?
5x squared and 10x, they have like I forgot what it's called, but is it lowest common multiple or something like of 5x?
Well, it's not quite lowest common multiple, but I think you might be you're sort of on the right lines with kind of looking at the numbers there, because you got the 5 and the 2 and the 10, and so you're sort of along the right lines in terms of looking at numbers like that.
I have an idea.
Someone just said they got an idea there. You want to go for it?
So for the 5x squared, you get 10x by multiplying the 5 by the power of 2 and taking away 1 from the power of 2. So that just leaves you with 10x.
So we've got 5x squared there. If we do 5 times 2, we get 10. And if we take 1 off the power, then we have like a power 1. I could put a power 1 there, couldn't I? We don't usually do that, but that would be okay. So if you multiply that coefficient of x squared by the power, and then take 1 off the power, just have a little look. Does that seem to work for any of the others? I would say, have a look at question 3. Minus 4 times 3. That's minus 12, isn't it? Take 1 off the power. That's 2. Okay. That seems to be working. Okay. And in fact, well, that is That is the quick rule for doing this, okay? Is that we multiply, whatever the coefficient in front of the term is by its power, and we subtract 1 from the power. That's a sort of quick way. If you think about, I'm going to add a few little things here just for the sort of special cases here. 6x is really 6x to the power of 1, isn't it? And it becomes 6, because if you do that, well, 6 times 1 is 6, and then take away 1 from the power, it's x to the power 0, and x to the power 0 is just 1. So just 6 times 1. So we can just write 6. We're not going to write x to the power 0. That's really just what happened with this minus 7x here. To get minus 7, the exact same thing as we just done on question 2. And then, what's the special bit here? The plus 4, that just seemed to disappear. Okay? And really the reasoning for that is, well, have a look at question 7. Y equals k, y equals a constant. And for y equals a constant, if you drew that graph, that's just a horizontal line, right? Y equals 3, you just draw a line at 3. Y equals minus 2, you just draw a line straight across at minus 2. And, a straight line across, a flat horizontal line, has a gradient of 0, doesn't it? So all your constants, when we differentiate, they're just going to disappear because they don't really add anything in terms of the gradient because they're just the horizontal line part of it. Okay? And if you think about an x cubed curve for question 5, if you stick plus 4 on it, it doesn't change the shape of the graph, does it? It just moves it up. It moves it higher. It doesn't change how steep the graph is, the shape of the graph. It just moves it up. So you've got those sort of aspects of it there. Okay, so there's 2 parts to that, and I know we're running short of time. There's what we call differentiation from first principles. And that is you guys using this formula and doing all that simplifying and sort of all that nice algebra that we started off with. Okay? And now looking for, you've got to be able to do that. That it could literally be an exam question. From first principles, differentiate this function. And you've got to do all that. You've got to show all that working out. You've got to put limit h tends to 0 on each step. You've got to do all that stuff. For other questions, they might want you just to find the gradient because then you're going to do something with it afterwards. So we like the sort of quick method that we've just been discussing here, where we can go, well, 5x squared, 5 times 2 is 10, take 1 off, it's just going to be 10x, right? We've got 10x, now we can do something else with it. Okay? Okay, so those are the 2 little aspects. As I said, it's been quite quick, and in terms of a lesson, we usually spend a lot longer on that, and obviously we would still be spending time on that when you join us in September. That's not it for that. You're going to get lots of time to practice that and have a look at differentiation again. We've only got a couple of minutes left. Lesson's due to finish at 10, so we've got a couple of minutes. So if anyone's got any questions or anything, or if there's anything they didn't get to find out that I might have missed or anything like that, I'll hang around for a couple of minutes. We've got another lesson at 10:05, so I've got a few minutes and some questions. Otherwise, thank you very much for coming. Thank you for contributions. I'm sorry I couldn't see who it was contributing at the time, but thank you very much for those. Some great answers, and I look forward to seeing lots of you in September. And don't forget about those summer tasks. So, bye everyone.
Bye.
Yeah, Nathan, you'll be sent them through the sixth form team. It'll either be Miss Pride or Mr. Greenhouse, but it should all go into teams as well. So I think you should find all that quite easily. All right.